Hello, hello. Mic's on చేస్తున్నాం.
ఏమో పంపించాలి. అందరికీ ఉంది సార్.
Ready? It has to start. I have to report to SAE. Chennai. And then running.
Hello. Let's.
కిందకి Good evening. Good evening, my dear students. I would take the privilege of inviting today's resource person for the guest lecture, and it is also a SAE lecture, which we call it as SAE lecture meeting for this particular month of July. Dr. Gurraj Telsing. I request you all to join your hands and clap for the person. He is scientist E at Advanced Research Center for Powder Metallurgy, which is very nearby to us at Balapur. And also he is one of the executive board member of Hyderabad, SAE Hyderabad chapter. He is holding the position of vice president, vice chairman, I beg your pardon, vice chairman. And he is also instrumental in building Hyderabad, SAE Hyderabad chapter. In fact, I have joined as a SAE Hyderabad member under his stewardship. He has given me a lot of prominences and most privileges that, this institution, whenever we used to ask him, sir, can we come down and, use a facility or any help that you can render to us, he used to always invite us and join us at this particular point. Sir, I take the privilege of inviting you on to the dais, and please take the lecture. Thank you very much.
Take some photos and upload.
Yes, sir.
It's online now?
Yeah, it's online. It's also YouTube.
Huh.
We are streaming in YouTube.
Yeah, so I have to be little
Yeah.
tune it accordingly. क्या वो क्या कर रहा है? Recording online.
Yes. Once again.
Is there no issues?
So I have to stand here only, right? I come now.
Yes.
Okay.
Sorry.
So my voice will my face will not come, right?
Yes, sir.
This online is creating problems. You can't be more interactive. Anybody registered online?
Online, I have reached.
So leave it. Why online is struggling so much?
Inkadu, Vijay. So, well, if you have an issue, no problem.
No problem.
It's
Technical problem.
it's almost completed.
नहीं हो रहा था छोड़ दो.
नहीं हो गया.
Hello. Audible? This one. Hello. Yeah. Good evening, all of you. So second year, third year students, right? automotive engineering. Yeah, I'm going to present today on metal additive manufacturing. I hope all of you heard about 3D printing, plastic 3D printing. You have system you saw somewhere, right? In campus. Yeah. So what you see usually is it's already there. So it's a plastic 3D printing. So plastic is used, material as a plastic, and used to they melt it and they squeeze it out in a nozzle and move it like you move a pen for a drawing in a white sheet. So it will be moved and that plastic will get deposited the way you move. Then layer upon layer you add and you will get a 3D shape, whatever shape you are printing, right? So when it comes to, if you change the plastic, when you say plastic, where all you can use? So it has its own limitation as a material, right? So if you go for engineering like automotive parts and all, most of them are what? Metal, right? So when it comes to metal, I said plastic melting and then squeezing it out by a small nozzle will give you a material to deposit, right? So when it comes to metal, so do you think what is the melting point of a metal, whichever metal, suppose aluminum alloy you take, what is the melting point? Anyone? Somewhere around 6 to 7, 650, 700, they melt up to 750 also they take it. Again, it depends on what kind of viscosity, melt viscosity you want, right? So now given aluminum alloy, do you have any nozzle which will squeeze it out at 600, 650 degrees centigrade to print it like a plastic you saw, plastic system you saw? Not possible, right? So you should have a ceramic nozzle and you should have a system accordingly to handle such a temperature and all. So 600 is too high, even 200 degrees centigrade is too high for your information. So when it comes to metal, you need some different kind of technology altogether to realize things the way you want, like 3D printing. Same we'll call 3D printing, but you need a material to be deposited in some way. So we are going to talk on that aspect. There will be some up to certain level I'll take plastic also as a material, but after some 3-4 slides I will shift to metal alone. Okay, so it will be interesting for all of you because you are from second year and third year. You can go and watch after this talk in YouTube or any resource you have to understand more. Okay, so if you have anything, if you want to see machine by yourself, you are welcome to our organization ARCA. We have a system running there, metal, what I am going to show you people. If you are interested and you want to see some more of it, so it's open for you. Okay, so let's move on to, I hope all of you know, when you say 3D printing, plastic 3D printing, I hope you know conventional manufacturing. What we do usually, we remove the material to give the shape, right? So let's call it as a subtractive manufacturing. Is it okay? So opposite to subtraction is addition. So what we are talking is additive manufacturing now. So you are machining, CNC machining and all. You take a rod and you machine out, remove the material to give a shape to rod, right? So here we are doing opposite. You have nothing. You have material in different shape, different form, and we are adding that to make the component. Like constructing the building. So land, there is nothing, right? Empty land, empty plot. So you will add bricks and your cement mix to build the wall and achieve the 3D shape wherein you can walk inside, right? All those things you can do. It's nothing but 3D shape of the construction, right? So similarly, you are bringing the material from different source, add them to achieve the 3D shape. So similarly, when it comes to engineering components, what is more precision? Precision means engineering design, drawing, and dimensions and material performance for the stated application is what we have to look for. So keeping that in mind, so you have to achieve the shape to the ultimate shape you want. Because when you say 3D printing, so you can't do many intensive post-processing. Post-processing, you understood? Means after building, you take the component to give a final shape, right? So if that is too much, then why I am doing all these things? So you have to find a technology which will give you minimum post manufacturing efforts, right? So that is called high precision 3D printing, right? I will show you some technologies which will categorize depending upon the level of post processing and all. Am I moving the slide? Down only I am pressing. Yeah, next slide. I'll put it here. Yeah, it's okay. So you can see there, whatever 5 or 6 things what I showed there, you can't imagine those things possible by conventional manufacturing. Okay, can you see there? There is a nozzle which has a inlets coming out like a tube coming and it's not welded. It's one piece nozzle. And the second thing what you are seeing is a part integration. So there are many union joints and many weldings in the component which you can eliminate now. Why they are welding 2 components? Why can't they make them one piece? While machining itself you make it one piece, no? Why you have to weld? Why? Because conventionally you can't manufacture as a one piece. It's a limitation of conventional manufacturing. You can't have hollow inside while manufacturing. So you have to make 2 half, then weld them to make a hollow sphere. Right? You can't make one hole and dig all the material inside from one hole. So you should have 2 half or maybe some other design where you will have major portion will come from other side and assemble and make it. So if you see many of your bike components, they are all assembled in some other way, and they put washers, sealings to avoid leaks and all, right? For your hydraulic, oil reservoir, what you have in a brake system. So that has 2-3 pieces, but they can't make it in one piece. Even it is a cast part. Making in symmetrical part or some partition part, they can make in casting. But if it comes to the asymmetric part, it becomes challenging for casting also. So die life, the mold life, all matters depending upon how you design the die, and for that such integrated part, it will be difficult to design a die. So they compromise with the design. They break the design into 2 or 3 pieces. They make them in separately, and then they will put an effort to join them or assemble them. There you will see many problems, leak problem with time, or weld failures, all those things. So part integration is one where you can look into additive manufacturing, right? So these first 2-3 slides I will spend time so that you will understand why you are here and why you should listen to it. So that rest of the slides, it's specific to some application. You can find many application and look into open source and find orient yourself. So these are the things why it will put you in this technology, right? Next thing, you can see a conformer cooling channel. Can you see that image there? It has a channel inside, spiral channel. So that is also one piece. So conventionally, if you see any design which has a cooling channel inside, that will be definitely in 2 parts. That to exactly where cooling channel is there. They'll make 2 halves of a channel and they'll put washer to avoid the leak, and they will join them and they will bolt them together. So that is too risky when it is high temperature. It may catastrophically fail, right? So all those things can be made in one piece. This is one such a nozzle. The nozzle what I am showing there, conformer cooling channel nozzle, that has at least 8 pieces which is there in my office used in one process. So we replace that with a 1 piece nozzle with such a design, which is possible by metal additive manufacturing, right? So next is the lightweighting. So it's a aluminum honeycomb what you are seeing there. You will see, when you say honeycomb, you will see ceramic honeycomb which is extruded. But metal honeycomb, can you imagine? You can imagine. There are some technology you might have heard. If you are interested, you can go and search metal foam. Have you heard foam? If I say metal foam, can you correlate? Means of aluminum foam, aluminum alloy foam, means it has so much porosity inside, interconnected holes. It's a foam. You just imagine how you will make. You will make a foam by take a soap water, do what is that? Blow in that and you will get a foam, right? Which will have air captured into the bubbles. But same thing if you do in metal at 650-700 degrees centigrade, you will achieve metal foam. It's a technology by itself. It's not that easy with the way I'm telling, right? So those are the technologies. So, but here what I'm showing you here is honeycomb with the porosity inside. So I can define the porosity. I can achieve the way I want interconnected porosity also, right? That technology is different, metal foam. This technology of achieving lattice structure and honeycomb structure is different. It's called lightweighting. There is something called dissimilar material. I will not stress much on that. So it's like, welding copper and steel, dissimilar material. If you have already one existing component on that, you want different material like conductivity, heat exchangers, fins. Only fins you want copper. Suppose you have some surface where from which you want to take away the heat. So if you have a copper fins there, you will remove material heat more fast, right? So this is something what I wanted to tell you. So you need a material, you need a source, energy source or binding method, and then you need a technology to bring them together. In plastic 3D printing, what you saw, you have a plastic as a material, polymer as a material, nozzle which is heating, giving heat to melt it is an energy source, and the system what you are seeing, the machine, is bringing energy and polymer together to make the 3D part. It's okay? Can you relate? So similarly, when it comes to any other material, you need a material in particular form, then you need a method to bind it, technology to bind it, and then you need something which will bring them together. That is a process, right? So with this, can you see here? Pointer? Do I have a pointer? Right. So there is a powder, there is a wire, there is a sheet, there is a liquid. So these are the different forms material can be. So if I say wire, it's a polymer 3D printing, what you saw 3D printing where polymer is used as a wire, right? So it can be a metal wire in metal 3D printing. When I say powder, it's a polymer powder or it can be a metal powder. When it is a sheet, it can be a metal sheet. I'll show you technology dependent. It can be a liquid also, right? So there is an electron beam as an energy source, laser beam. Pointer and lasers you saw, which you can red laser, green laser. So similarly, there are near infrared lasers which will focus the energy so that at that spot the temperature will be so high you can melt the material. Means without having furnace kind of thing, wherever you focus, only in that point you will rise the temperature. I am telling you focus means focus point of 1 mm, less than 1 mm, 800 micron, 600 micron, 300 micron, 100 micron also I am telling. So 100 micron circle, if you focus energy in that area, it will raise the temperature to the melting point of the alloys. Up to 1500 degree, 2000 degrees centigrade it will go. So when I can focus selectively melt one line in the full block of the metal, if you take, I can move a laser in that only that line will melt. Material in that line only will melt. Now you understood what I am trying to say? So similarly, when you spread the powder, if I run the laser, focus the energy beam on that with 100 micron, I'll get 100 micron melted line, melted deposit. Remaining all powder is loose. Only where laser moves, only that powder will melt. You are understanding this? I am using this technology, this understanding for making a technology or process for additive manufacturing. Right? Similarly, if I change laser to electron beam, electron beam? Yes? Okay. It's a energy source by generating the electrons and moving it at the high speed and then focusing it to get the required energy. That energy also can be used to melt the alloys. Okay. Then comes induction coil heating, induction hardening, right? So that is the technology. Then ultrasonic wave. So ultrasonic energy will be used to bind the material. Then there is a liquid binder. This is very simple, liquid binder. So you just, you know your inkjet printing. So what is happening there? So ink is being sprayed by micro nozzles. Yes? Sub-micron nozzles. So whatever if you write A, you reduce the size to 8 font size, that also will come. So to write 8 font size, you can't even use your pencil to write A to that font size, but it will do, the machine will do. What is there? there is such a fine nozzle which will spray such a fine droplets of a liquid which will be absorbed by paper in that pattern to show you that number. Yes? Can you imagine the technology? So same thing, if I remove the ink, I will put the binder. Okay? So now binder will get sprayed. On what? On a layer of a powder. Can you imagine? So layer of a powder, wherever binder falls, those particles will get binded. Okay? So now the features are like your printer features. Because when technology is there to spray the ink, the same technology can spray the binder. Now that binder will bind my powder, so I will get the shape I want. So if I do that repeatedly, fresh powder, then again spray, fresh powder, again spray. So each layer will get binded. So I will get the 3D model, a gray part. If I take that to a furnace, sintering furnace process and all, you will get the sintered part, which is a powder metallurgy method of achieving your engineering components. So most of the automotive components are powder metallurgy components, right? So those are done not by 3D printing as of now. They are done with a powder, tapping and then getting the shape and then sintering. So similar thing we can do by using the 3D printing, complicated shape, which is not possible by conventional powder metallurgy method also can be done. So that technology called binder jet technology. I will show you what technology will call what and why. Right? That is what. So UV light also used for binding the material. So that's what so these three columns you need. So fourth column is first and second they will bring under that powder bed, powder and wire, and liquid bath. So it's a platform where these two will come and enable you to achieve the component or whatever you are making out of it. Okay, so let's go to next slide. Yeah, here you can see here. So the last column what you are seeing in the tree, the last branch, is the entire in the world whatever is available for additive manufacturing, whatever you say 3D printing, additive manufacturing, all of them are categorized into those 7 classification. Okay, this is as per ASTM. Can you see there 2792? So as per ASTM F2792. So all the technologies whatever you say in 3D printing, they will fall one of these 7. So the previous slide I told you what all you need basic components of additive manufacturing. So when you choose one of them, powder, suppose if I go to back slide, here if I choose powder, there I choose a laser beam, there I choose powder bed, right? So that will give me this technology called where is that? Powder bed fusion. Can you see that? Additive manufacturing, powder based, then melting, powder bed fusion from bottom, third one, right? So like that, in that combination, that's why these trees are connected to show you how those 7s came. So all these 7 are basic principle are different, material wise different, and operation wise also they are different, right? So whatever I said, the molten, polymerizing, bonded object, melting and binding, right? These are all base methods. Those are all the method of binding. Then those are all the technologies. This is again same thing, kept only 7 of them. And what is the technology commercially known? This is what you will see if you go and search in the internet. These things will come with your intensive second level of search, but that you will see SLM, EBM, DFAM. EBM means electron beam melting. SLM means selective laser melting. So laser melting, laser as an energy source to melt the material. Electron beam as an energy source, EBM, right? So those are the things what you see, multi-jet printing, laminate object, LOM. So for that information. So I'll not spend much time. You can go and see that in any source available, open source. So this is the technology, what I was telling you, all those 7 things you see there, right? So A is something related to light source used to print that. Can you see that? Watt polymerization. Okay. So there what they did, polymerization? You know polymerization? Even though you are automotive, you should know polymerization, right? So monomer, if you put some polymerizing agent or method or heat source, it will start connecting, networking, and that's called polymerization, right? Monomer become polymer. So that can be controlled and selectively polymerized from the monomer using the focused laser beam. That is a technology, right? So can you see that red line there? That is guiding the laser in the monomer path. The tank having monomer, you just move the laser where the laser is focused inside the monomer path, there only polymerization will happen. So that will become the part, remaining monomer will come out as it is, so you will end up with a part in the bath, right? So that's what they are trying to show there. Then B technology is that it's a powder bed fusion. So there is a powder on a left side tank that will be moved layer by layer to the other side by spreading. So as I told you, there is a laser powder bed, then you are moving the laser energies, focused one, in the pattern you want. So powder will melt and get attached to the previous layer. So that's how that technology is happening. So the other z-axis will move down, then again powder will spread, again z-axis will move down. So you will get the part inside the loose powder, which you will take out later. So this technology we have in ARCI in my lab. So you can visit and see this happening, right? So this is the technology where material jetting, I told you the inkjet printing. So there, instead of ink, instead of binder, your material it will come out. So like construction, have you heard 3D printing of civil structures? That IIT Chennai recently in India and Japan, Japanese companies are there, many companies. They are making a house by 3D printing. Have you seen any videos? You go and see, search in YouTube, you will get a nice videos. What they do is they take a big nozzle of a cement mix. They will just move the nozzle by a big load carrying anchors. So that will move and nozzle will move, and they will make exactly the wall shape, and they will build the entire house in 3-4 days. But the cement used is a special cement which is having a high curing time and a very less curing time, so it will cure immediately. So that's a special composition of a cement they use, not the normal cement, so normal mix. So they achieve the building in a very less time. So that is what is a material jetting. So you are giving the material out. Like, have you heard making a human organs, animal organs by 3D printing? That is material jetting. So the material mix of matching human organs composition is squeezed out of a nozzle, and you move the nozzle like FDM machine, then you will get that shape, right? So that is the another technology. It's called binder jetting. That's what I told. Instead of ink, you spray the binder, but there will be a metal powder layer below which will bind that. That is something similar to powder metallurgy method. But before going into powder metallurgy, sintering and all, you just do the 3D printing of the component and get the shape, then follow the conventional method of powder metallurgy. Then this technology called material extrusion. It's FDM, your plastic 3D printing. What you saw is the E here, and that is a sheet. Can you see there is a F1? There are two side rollers are there, right? The sheets are being taken away. The sheets are fed from the other direction, and you move the laser. So thin sheet, then move the laser. Wherever laser moves, the sheet will get attached. That portion will attach to the previous layer, and the sheet is free. You just take it out. So like that, you can add sheet on sheet by melting and fusing that to the previous layer. You will get the 3D shape. But ultimately, the basic question you should ask here is, when I take the component out of any of these technology, can I use it directly? Which technology will give me direct part, right? So that is, if you are going for application. But as of now, you just understand the technology. Right? These are the 7 different methods to see the additive manufacturing, right? So this is again metal additive manufacturing, same thing put in more complicated way. So don't worry about it, but the basic 7 classification, if you understand, that is good. So can I brief it now? So you have material in shape, you have method of binding, material for binding them, material, then you have technology to bring them together. So if you understand these 3, if you make a different combination of these, you will end up with a 7 classification. Clear? Right. So this is what we have in ARCI. Right? Now I am focusing only on metal additive manufacturing, which I showed you, powder bed, laser powder bed additive manufacturing, right? So we have that system. You can see the image there. Then we need this post processing. That's what I asked you. Can I use the part coming out directly to the application required? So whenever I say I am selectively melting the powder and solidifying it, that is nothing but a rapid solidification. So very high cooling rate. You will not get the equilibrium microstructure there. So you may end up with the entire component with so much brittle and sometime different microstructure. So that may not be suitable for your application. You may have to do heat treatment. So you need a material expert who will understand the microstructure, who will suggest you suitable heat treatment, right? Then you heat treat the component and then use it for the required application after achieving the required properties, right? So that's what we have, those facility for such things. Then we have characterization. Sometimes you have to understand the material if you are developing the process for new material. So all that facility. We have atomizer also. When I said powder bed, I need powder, right? So metal powder. How I will get metal powder? So there should be a process to make the powder, right? So what kind of powder? Powder has to be spherical. I have a slide. I will show you on powder how it should be. It should be a spherical. Why spherical? Because I am spreading. So if I want to spread the powder, as spherical it will spread smoothly, right? Otherwise you will get somewhere one line. Can you try? Just take a sand and make a thin layer of sand. It's very difficult, right? Because you have odd shaped particles, you have different size particles. So you will get a line, you may get some slope varying and all. But here when I am talking technology of 30 micron, 60 micron layer, how much I should be as close as to the what I am thinking. So you can imagine the technology now, right? So for that we need a spherical powder for this technology. So we have atomizer. We can make take a ingot and atomize the material, melt it and then atomize. Atomization is what? Atomization is not AU. I am telling ATOM. Atomization means small particles. If you take a water in your mouth, if you do blow it out, so you will get particles of small droplets, right? Same thing, you melt the alloy and you allow it to come out of a orifice and then give flush of inert gas. So you will get all that melt spreading into the small droplets. Depending upon, you can control the pressure and all. On that you will get a different size particles. So that you classify, classifier, separation, screening, sieving and all. Then take the powder particle size you need, right? So that's how the metal powder are achieved. This can be done in water atomization. They call water. Inert gas atomization they call. There is something called spark plasma atomization. There are different technologies to get the powder. Depending upon the technology what you use, you will get the quality of the powder and cost of the powder and material also you have to choose accordingly, right? Yeah, this I will not spend much time. So this is there. If you want to see these machines, these two machines are running in our ASEA. You can visit. So let's not spend time on that. It will be too much. So next. Yeah. So here what you have to decide where you will sit in this entire cycle of additive manufacturing. So additive manufacturing starts from where? Anyone? 3D printing starts from where? Design, right? You have a 3D model. So who will design that? Design engineer with what understanding? Application understanding. Software, anyway you can use anything. You can make your own hand drawing also, no need of software, right? So software is one part, but you need application in mind for what you are designing. And you have to decide material also, right? So once that is done here, so there you need a design engineer with the design knowledge and application knowledge. But when it comes to the next stage, additive manufacturing, then you have to think from additive manufacturing point of view. Just now I told conventional machine, CNC machining if you are using, I am digging the material out to give a shape. So I can't do all the things. So that's why what I'm doing, I'm cutting my design into two parts. I'm making it possible by conventional methods and then join them. But when it comes to additive manufacturing, I don't have to do that. So that means what? You need a different prospect. So you need a person somewhere sitting in between who will know the additive manufacturing possibilities, who will know the requirement, and he will match them and come up with a new design. That is called DFM, design for additive manufacturing, modified for additive manufacturing, right? So conventional design is okay to certain extent, but you have to orient yourself to additive manufacturing. So if you know what technology out of those 7, what you are going to use, so accordingly you have to modify your design and make it, design for that technology, right? So we do that. I will show you some case studies. You will understand. I hope I will get time to show you in detail. So that is the optimization. Then there is a slicing. So once you get the design for the technology what you want to achieve that component, then you have to understand which orientation. Means I can build this mouse like this also, like this also. So how I will build? So I will slice it like this, or I will slice it like this. So if I do it, now Z is too high. If I do this, Z is less, but area is too high, right? And I may need supports also sometime because it's a hollow. So inside it will take support. So I have to think, if I put it in a certain angle, suppose. So now Z and area is compromised per layer. Per layer area you have to see. If I cut it, the area is different. If I cut it, area is different. So you have to imagine all those aspects and think where all you need support. So when I say support, you just imagine simple thing for your level and your understanding, initial understanding. If I'm building a hall, there is a slab. For slab they give support, right, inside. Same thing. You just correlate to that and bring down to engineering component. So now you have a small component where your finger also can't go inside. So you are giving support. How you will remove, right? So that also you have to consider. Means how after component is done, you have to remove that. So you have to think of how I will remove. Then you design that. Then you add in the 0 stage itself, in the design stage itself. I have not yet gone to the machine. I am just before the machine. So there you have to slice. Before slicing, you have to put supports. Then you have to slice. Then you have to take that as a input for your machine. So that third blue, you will have your machine file, which will go to the machine. And there itself, you will decide the material. You will know the material. So accordingly, you will set the parameters, best parameters and all. That is optimization of parameters, right? So that is the additive manufacturing system. Then it will goes to finished part. Means you have to remove support structures now. If some dimensions you added extra, you have to correct them here. Sometime you may have to do that, right? So then it will go for testing and validation. So you can see their interconnected loops, they are coming back. So any point of time, you will initially, now this technology is for every application, you have to start from 0. So every design you have to think, if material change is there, you have to think too much. If material is same, if design is changed, again you have to reconsider everything, right? So that's what it is saying. Now, as an expert, as a knowledge person in this technology, you have to choose where you will sit. If you are on additive manufacturing green box, you are a process engineer, right? So if you are here, you are a design engineer. So if you are in between somewhere, you are a designer for additive manufacturing, right? And there is a one person called material expert. So he may come in the beginning also, in the finished part, post-processing also. So there you need heat treatment, metallurgical aspects are there, right? Then comes testing and validation. That is again another vertical where people can contribute, right? So this is what I was telling powder. Powder has to be spherical, the first one, because aspect ratio should be as close as 1. So we prefer spherical because it will spread, and also when it spreads, you get a 60 micron layer thickness. It has to have good compact density. Means it should not be so porous. It should, there's all big particles will give you no gap between the particles. So you should have uniform distribution of a small and big, so that your packing density will be, for that layer thickness will be, will not have too much air entrapped in it. So that's why we choose spherical with a defined size, particle size distribution. So you can see the different types of powder shape. Some are agglomerated, some will have satellite particles, some are non-spherical. These things will not give you required property. You may have to optimize too much. Even though you optimize, repeatability may be the issue, right? So your feedstock, the powder, should be as uniform as possible, as repeatable as possible. Okay. Next, yeah. these are all the different materials. I hope you will come to know as you come to final year different materials. They may hear all these materials. I don't know. Yeah. So there are iron Fe alloys, aluminum alloys, titanium alloys, nickel based alloys, cobalt alloys, copper alloys. There are many things. There are some challenging alloys. These are the alloys which people are attempted. Some materials are already established. Some materials still under development. To tell you that okay, these are the parameter window. If you use this parameter, process parameters, any design you give for that material, you will achieve required shape and properties. Then they will also tell the post processing, post heat treatment conditions also. Then if you do that, if you use that material, you will achieve the properties what they are stating. So like that, now for every material, all material suppliers are making such a database. And if I am buying the material, I will see that okay, it's ready to manufacturable or not. Have they done already some experiment on that or not? Right. So those things you have to see for the materials. These are the material which I listed. Right. So same thing what you saw before. These are all different stages. If I have some engineering component application in hand, the first column is different components what we did in our lab. Right. So if you go at a different stage up to testing and validation, can you see there are 4-5 of them have reached the validation stage, right? It's very difficult for new technologies to reach, on towards the right as possible. Means you're doing some real contribution, right? So next slide. So I will skip this. This is whenever you have new material, you have to follow this, all these stages. So this is what we do, right? So for different material, we follow all these things. Then whatever publication we say, journal publication will come from this work only, right? And this is one example. Can you see that wall block there? The wall